Hello, Math 113. Welcome to part 3 of section 6.5, which is all about complex numbers and DeMoivre's theorem. All right, so this again, part 3, and hopefully it's the final part. I plan on it being the final part, and maybe it won't last more than 30 minutes. Now, what we talked about in part 2 was actually DeMoivre's theorem, which is raising a complex number to a power, but doing that while it's in polar form instead of doing all the expanding you would have to do in regular complex number rectangular form. And this brings me to where we left off, which I think is example L, and we were asked to use DeMoivre's theorem to find the power. We're supposed to write the answer in rectangular form when we're finished. Now, if you look at this, you'll notice this is in rectangular form now. And if we were to expand 1 minus I to the 5th power using rectangular form, we would have to write that out 5 times, 1 minus I times 1 minus I times 1 minus 5 times, and either use some method of expanding binomials or FOIL it out. And that's going to get extensive and long and probably incorrect because it's so easy to make mistakes. If we use DeMoivre's theorem, we first must write this in polar form. So I cannot use this until this is in polar form. So that's step 1. I've got to write 1 minus I in polar form. I'm trying to get my pen working right. There we go. So 1 minus I. Remember, the first thing you have to do is find your modulus. So what is R? Remember, that's the square root of a squared plus b squared. A in this case is 1, so 1 squared. What's b? Negative 1. Remember, you never use I values inside your modulus calculation or when you find the absolute value of a complex number. So this gives me I is equal to, 1 squared is 1. Negative 1 squared is also 1. That gives me the square root of 2. I also have to find my argument, which is theta. So tangent of theta is equal to b, which is negative 1, over a, which is 1. So I'm solving the equation tangent of theta is equal to negative 1. Now remember, that happens twice on the unit circle. Tangent is negative in quadrant 2 and 4. So that angle right there, which is one of your over 4s, or that angle right there. So here's the deal. It helps to at least have a visual of 1 minus I graphed in the complex plane. That's positive 1 and negative I. We're talking quadrant 4. So this is the angle 7 pi over 4. Or you could do it in degree form. Would you like to work in degrees? That's easier for a lot of students. And it looks like your homework has a preference for degrees for this section. So that would be 7 times 180 divided by 4. A lot of you know this. That's 315 degrees. Okay? Since in the end we go back to rectangular form, it wouldn't matter if you did this in polar or rectangular. So now I'm writing just z. So I know that z is equal to my modulus, which is square root of 2. And remember, it's cosine of theta, which is 315 degrees, plus I sine of theta, which is still 315 degrees. So that is in polar form. So 1 minus I is equivalent to square root of 2 cosine of 315 degrees plus I sine of 315 degrees. Now, I need to raise that to the 5th power. So I am using this formula right here, folks. Okay? So what do? First of all, I raise square root of 2 to the 5th power. And then that's going to be cosine of 5 times 315 degrees plus I sine of 5 times 315 degrees. You okay with that? Okay, now how am I going to handle square root of 2 to the 5th? It's square root of 2 times square root of 2 times square root of 2. Let's think about that. There's different ways to think through that. That's 5 of them, right? These two are 2. These two are 2. and there's a square root of 2 left over. So you see that's 4 square root of 2. Okay, and then I'm going to multiply 5 times 315 degrees in my calculator. And I get 1,575 degrees. So cosine of 1,575 degrees plus I times the sine of 1,575 degrees. There we go. Can hardly read it, but there you go. Now that is in polar form. That's not rectangular form. What am I going to do to find rectangular form? Well, I'm going to type all this mess in my calculator, and I'm going to make sure I'm in what mode? Yes, degree mode. You can't be in radians to do this because we decided to do it in degrees because we thought that might be a little bit easier. So first check that and see I'm in radian mode, left over from another problem. I've changed it to degrees, and now I'm going to type in 4 times the square root of 2 times the cosine of 1,575 degrees. And it said error. Why? Because I didn't close out some parentheses. Still said error. Hold on. Okay, I think that error was all me. After I typed it in again, and I think I wasn't paying attention to closing out all my parentheses, I got -4. Y'all holler back if you notice anything different when you multiplied it. So again, I'm going to do 4 times the square root of 2. So 4 times the square root of 2. Now close out parentheses if you have parentheses underneath that square root. Times the sine of 1,575 degrees. Make sure you're in degree mode, and I got 4. Don't forget your I back there. That's still there. So -4 plus 4i is rectangular form of 1 minus I to the 5th power. Okay, as long as I didn't make any mistakes, I think it looks pretty good, then that's how you do that. All right, let's see what we got going on next. Okay, use another one. Use DeMoivre's theorem to find this power. Z to the 6th equals 2 times cosine of 20 plus I sine of 20 to the 6th. Hey, why don't you pause it, work through this, and let's see if we get the same result, okay? Okay, so I'm hoping that went easy peasy for you. Notice I'm bad about directions. It says use DeMoivre's theorem to find the power, but it doesn't say to write your answer in polar form or rectangular form. Really notice that. We're going to do it both here. So z to the 6th, remember you have to take your modulus and raise it to the 6th power. So z to the 6th is going to equal 2 to the 6th times the cosine of 6 times 20 degrees, which is 180 degrees, plus I times the sine of 6 times 20 degrees, which is still, did I say 180? It's not, it's 120 degrees. Okay, you're telling how many of those mistakes I make. 2 to the 6th. All right, what is 2 to the 6th? 64, right? Okay, 64 times the cosine of 120 degrees, plus I times the sine of 120 degrees. If your homework problem said to write it in polar form, you would be done. It seems like the majority of the time they want you to do something else with it, like write it in rectangular form. So that's what I'm going to do next. And because this is in degrees, notice, look, I'm not consistent either. I put parentheses around it here and not here. Honestly, it doesn't have to have parentheses. I kind of like parentheses because sometimes it's easier to tell what's going on, but that's appropriate, or that's appropriate. What's probably doesn't look so good is when one's in parentheses and one is not. So try to be consistent. I try, but sometimes I fail miserably. Now, let's write this in rectangular form. Again, what am I going to do? In my calculator, I'm going to type in 64 times the cosine of 120 degrees, and then I'm going to push equal, and I'm going to write it down, okay? What's the most important thing? Please make sure you're in degree mode and not radian mode. So this is going to be 64 times the cosine of 120 degrees, and I've got -32. This is going to be -32, and then I don't want to put plus yet because it might be minus, but I know I have an I next, okay? So I'm going to do 64, don't forget the 64 again because it distributes inside, okay, times the sine of 120 degrees, and I got, oh, not pretty, 55.4256. Now, I'd have to have more directions. It is positive, so I'm going to put plus, but, okay, now let me tell you what looks wrong with this. Let's just say we're going to round to the 10th place. You have to be told where to round when it comes out like this. But this looks bad, okay? And that's not degrees. No wonder it looks so bad. It's just 55.4, okay? But you put i's after that. Where you put i's in front is when you have a trig function or a radical back here. But when you have just a number, a decimal number, or whole number, real number, well, no. Square roots are real numbers, but we put them in front. Decimals, fractions, whole numbers, put the I in the back. Okay, so this is rectangular form. Okay. Now again, your directions are going to be more specific than this vague stuff I'm giving you. It's either going to say write your answer in polar form or rectangular form. And if there are decimals involved, it's going to say where to round. Sometimes they like you to round the tenths place. Sometimes they take it on out to the thousandths or even 10,000ths place. So just be careful with directions, please. All right, roots. And it turns out this is the real reason you're studying this, okay? Because it's probably not often, even in the math world, where you need to raise a complex number to a power. But on the other hand, solving equations, okay, finding the roots or solutions to an equation is where you will need this DeMoivre's theorem. Okay, so we did a problem. Did we just do this problem? Where we had 2 times the cosine of 20 plus I sine of 20 to the 6th power is 64 cosine of 120 plus I sine of 120. Let's check that. Sure enough, 64 cosine of 120 plus I sine of 120. That was in polar form. Notice I didn't even take it to rectangular form here. Now, why am I showing you this? Because I want you to realize something, okay? We say that the original I, 2 times cosine of 20 plus I sine of 20, not raised to the 6th, is a complex 6th root of 64 cosine of 120 plus I sine of 120. So this inside part, before we raised it to a power, is a 6th root of this complex number over here. Okay? There's more to this story. It is one of 6 distinct, that means they're different, complex 6th roots of 64 cosine of 120 degrees plus I sine of 120 degrees, okay? So that number, 64 cosine of 120 degrees plus I sine of 120 degrees, remember that is just the polar form of some complex number, and it has 6 distinct 6th roots. That is hard to say. All right, keep going. In general, if a complex number z satisfies the equation z to the n equals w, okay, so you have some complex number raised to a power equals some other number, we're just going to call it w, then we say that z is a complex nth root of w. It is one of n distinct nth complex roots that can be found using the following theorem. So here is the theorem, and it's DeMoivre's theorem again, working backwards, okay? So notice, let w be a complex number in polar form. As long as w is not equal to 0, w has n distinct complex nth roots given by that formula. Okay, so notice one's in radians, one's in degrees. It's the same exact formula. So you take the nth root of the modulus. Okay, so notice that's in front. And then you do cosine of your angle plus 2 pi k. Now your k is what root you're dealing with. You're either dealing with the 0 root, the first, second, third, fourth. N is the nth root. Okay, don't worry, we're going to use this formula and you're going to realize it's a lot easier than it reads. Okay, and this applies to degrees as well. It's exactly the same formula, but 2 pi k turns into 360 degrees, right? Because 2 pi is all the way around the circle, and so is 360 degrees. Okay, so just bear with me. Let's actually use this formula. It says find all complex 4th roots. So that's going to be important. We're doing fourth roots in polar form and theta in degrees. So very specific directions here, like I should be given all the time. So in polar form and theta is in degrees of 100 cosine of 5 pi over 6 plus I sine of 5 pi over 6. Then plot the 4 complex roots in the complex plane. Now it's crazy, they give us radians to start with, but I'm going to follow directions. We're supposed to do this in degrees. All right, you ready? Okay, so we have, first let's use this general formula. Why did I pick that one? Because we're talking about in degrees, right? Not radians, but degrees. So we have z sub k, and we're doing, what's our k? Well, we're doing the fourth root, so let's just write z sub k equals. Now that's the nth root of r, so that's going to be the fourth root of our modulus, which is 100. So the fourth root of 100 times the cosine. Now 5 pi over 6 is in radians, but we need it in degrees, so let's change this to degrees. Remember, that's 5 times 180 divided by 6. And I get 150 degrees. So this is going to be 150 degrees, I'm just using the formula, plus 360 degrees K divided by n. Remember, n is the fourth root, so n is 4. Plus I sine of the same degrees. Notice I put parentheses again, and I didn't on the other one. Let's be consistent. Okay, so that's going to be 150 degrees plus 360K divided by 4. That's the general formula. Okay? Now, let's keep going. And we're finding 4 distinct roots. So here's how you do this. You do z sub 0. Then we're going to find z sub 1, z sub 2, and z sub 3. There will be a z sub 4, because if it's 4 roots, that's all 4 of them. It's 1, 2, 3, 4. You with me? So we've got to find the fourth root of 100. Okay, we got to evaluate the fourth root of 100. Now, to me, it helps when I think about fourth roots. It's like a square root of a square root, right? So that's like the square root of 100 under another square root, which is really the square root of 10. Do you see that? So on this next line, I'm going to go ahead and write it as the square root of 10. But now, this is z sub 0, which means in every situation where there's a k, k is 0. So this is going to be the cosine of 150 plus 360 times 0. I'm going to write it out this time. Divided by 4, which is really just 150 divided by 4. So that's I sine of 150 divided by 4, right? Because you would do exactly the same thing here. Those angles are always going to be the same. So to wrap this one up, the z sub 0, you're going to get the square root of 10 times the cosine. Now, what is 150 divided by 4? I'm going to my calculator here. You can probably hear me moving around. And it is 37.5. Okay, so cosine of 37.5 degrees plus I sine of 37.5 degrees. I'm sorry for the short space. Get it? Okay. The next one, still square root of 10 in the front. This is always going to be the same for all of them. They will all be the square root of 10 for the modulus, because you have to take the fourth root of whatever the modulus is for your W value. But now what's going to change is the angle. So this is going to be the cosine. Now I've got this time, that's 150 degrees plus 360 degrees times 1 divided by 4. Plus I sine of the same thing, okay? Which again is 150 degrees plus 360 degrees times 1 divided by 4. That's going to equal the square root of 10 times, now 150 plus 360 is 510 divided by 4 is 127.5. So you have cosine of 127.5 degrees plus I times the sine of 127.5 degrees. Okay, these are four distinct roots. So this is the first root where there's 37.5 degrees. This is the second root with 127.5. Let's find the third root, which is called Z2. So that's going to be, I put in equals. There's not an equals there. There's a parentheses and a cosine. I'm going to try to write a little bit smaller. This is cosine of 150 degrees plus 360 times 2 divided by 4 plus I times the sine of the same angle. 150 degrees plus 360 degrees times 2 divided by 4. That's going to give me the square root of 10 times the cosine. Now here I go. So this is 150 degrees plus 360 times 2, which that gives me, I typed in something wrong. So 150 plus 360 times 2. That gives me 870 degrees divided by 4. That gives me 217.5 degrees plus I times the sine of the same angle, 217.5 degrees. And then the last one, Z3. Okay, that's going to give me the cosine of 150 degrees plus 360 times 3 divided by 4 plus I sine of that same angle. I'm going to be lazy and not put it. So it's going to be the square root of 10 cosine. And in my calculator, again, I'm going to type 150 plus 360 times 3. That gives me a total of 1,230 divided by 4 is 307.5 degrees. And that's going to be plus I sine of 307.5 degrees. Please forgive me for the handwriting, but I think you're following me, right? Okay. That is your 4 distinct roots. Now notice the directions for this problem say, then plot the 4 complex roots in the complex plane. So we found all the 4 roots in polar form, but I'm supposed to plot these in the complex plane. I really didn't give you the easiest problem to do that, but I'm trying to make a point. So I'm going to do the best I can to plot these in the complex plane. I'm going to have to shift back and forth from a complex plane that I draw on my own and trying to come back and look. Now we know that the modulus for all of these is the square root of 10, okay? But I want you to take a look at the angles. And again, I could have picked easier angles to deal with, a problem that had easier angles to deal with than this one, but it's still going to work out, and I want you to see what's going on. So I'm going to make this simple. Complex plane. Ooh. Hold on. There we go. Complex plane here. I'm not even going to put a scale on it because making square root of 10 to the right length is going to be an issue. If I really wanted to do this correctly, here's what I would have to do. I would need to change the cosine of 37.5 degrees and type that in my calculator times the square root of 10 and then do square root of 10 times I sine of 37.5 degrees to change it to rectangular form to see exactly where to do it. As a matter of fact, I think one of my other problems has us change this to rectangular form. Let's try it this way first. Okay, so let's think about where in the world is 37.5 degrees. Okay, we know 30 degrees is right here. 45 is right here. So bear with me while I guess. No, please don't move like that. Bear with me a lot. Okay, my line's not doing right, nothing's doing right. Okay, 37.5 degrees. And so if I were to plot that point, remember it has to be the angle 37.5 degrees, this length would be the square root of 10. Okay, and that would be 37.5 degrees. Now let's take a look at my next angle. My next angle is 127.5 degrees. Now picture, where is that? You know, 90 degrees is straight up, due north, so to speak. 180 degrees is due west. 127.5. Well, even moreover, how does 127.5 relate to 37.5? Well, it's 90 more degrees if you subtracted them. So that helps me a little bit. And that is also the square root of 10. And again, this angle from here to here is 127.5 degrees. Okay, again, bear with me. I'm trying to make a point. Okay, the third, okay, that's Z2, which is the third distinct root. 217.5 degrees. It's still a modulus of a square root of 10, so how far out I go is exactly the same as the other two. How do 217.5 and 127.5 relate? Well, if you subtract them, it should be 90 degrees. I'm going to check just to be certain. 217.5 minus 127.5. Yeah, that's 90 degrees, so that's going to be easy to draw. So that's exactly 90 degrees. Oh, and it's 180 degrees from that one. It's not supposed to be doing what it's doing, y'all. Okay. Apologize. All right, there we go. So that length is the square root of 10. That's 90 away. That doesn't look perfect, but I'm just going to go with it. And that is 100 and, was it? No, 217.5 degrees. Okay, let's look at the fourth one. Again, bear with me. I'm trying to make a point. 307.5 degrees, the modulus is still square root of 10. So what is that telling me? How far out I go is the same length, except I'm going to 307.5 degrees. Now, how does 307.5 relate to 217.5? You guessed it, it's 90 away. So if I start here, I'm going out a distance of square root of 10. And if I draw my angle all the way around from here to here, that is that, I can't remember it for nothing, 307.5 degrees. And that is also the square root of 10. Now, here's what the point I'm trying to make. If you have 4 roots, they are going to divide the circle up into 4 equal parts where each one is the same length, which is equivalent to your modulus, which is kind of interesting. Okay, so if I looked at another example, this is not your problem that we just did. This is a different example that's a lot easier to look at. But these are 4 distinct roots, so this is another 4th root problem, and look how they're all 90 degrees apart, or pi over 2 apart, okay, and the modulus is all 2 in this case. If it was a 5th root, it would divide the circle up into 5 equal angles. So it's kind of cool, something to think about, maybe a way to check your roots to see if they're correct. Okay, finally, and y'all, I don't want to do this problem so bad because these just get tedious, but find all complex 4th roots in rectangular form. Now notice this is the problem we just did. It's the problem that took up the whole page where we found the 4 distinct roots in polar form. It's the problem that I just graphed the best I could without going into super detail. Now they want us to change it to rectangular form. Let's talk about how to do it and maybe don't do it. Okay? How would I change these 4 guys to rectangular form? Type it in my calculator. Okay, let's do one of them in red anyway, just to say we did it. Okay, so it would be square root of 10 times the cosine of 37.5. So in my calculator, I'm going to do square root of 10, close out the parentheses, that's where I went wrong earlier, times the cosine of 37.5. What's the most important thing? You better be in degree mode. Okay, so I got 2.5, y'all, that's rounded. Went ahead and round to the 10th place. That's what the homework typically does, but not always. Be careful. Plus I, and then I also have to do square root of 10 times the sine of 37.5. Okay, so the square root of 10, which is not going to be the same as the cosine, times the sine of 37.5. close out those parentheses, 1.925, which would be 1.9. Now, I'm not really supposed to put the I before it if I'm dealing with decimals, so I'm going to say that's going to be 1.9 I. And that would be that one changed to rectangular form. I know you could do the other three just as easily as you did that one, so I don't want to waste your time doing all four of those. But rectangular form versus polar form. Rectangular form, you just type it in your calculator and see what it is. Okay, so we did that. What is this problem? Okay, now this one is some work, and I think this one is worth doing, and then we're going to call this one quits. I've already gotten to 30 minutes also, because these last problems really take a long time to do. It says find all complex cube roots. That's important. We're doing cube roots of 1, the number 1. Write the roots in rectangular form. So when we finish, this needs to be in rectangular form. So we've got to do all the things. We don't have to plot it though, but you can imagine what that relationship would be. They would divide the circle up into 3 equal segments, all the same length. Okay, so our number, W, this is what you would call W, is 1 plus 0 I, right? It's the number 1, which is actually a real number. It's an integer. It's a whole number. It's a counting number, but it has no imaginary part, so plus 0 I. All right, now I'm supposed to change that to polar form before I can do anything to it, okay? So I have to find the modulus, which is going to be the square root of 1 squared plus 0 squared, okay, which is the square root of 1, which is 1. I also have to find the argument. Tangent of theta is equal to the b value, which is 0, over the a value, which is 1. Now, where's tangent of theta equal to 0? What angle? Well, that's 0 degrees or 0 radians. Anywhere else? How about pi? Pi radians are 180 degrees, except when you plot 1 plus 0 I, it's right here, which is right where 0 degrees is. So our omega now, or W, is in polar form, is equal to 1, which is our modulus, cosine of 0 degrees plus I sine of 0 degrees. Okay, now we're supposed to find the cube root. So our general form is z sub k is equal to the cubed root of our modulus, which is 1. And then that's going to be the cosine of 0 degrees plus 360 degrees k over 3 plus I sine of 0 degrees plus 360 degrees k over 3. And then we have to do our distinct roots. So z sub 0, z sub 1, and z sub 2. Remember, there's 3 of them. So the cubed root of 1 is 1, always. We don't even have to have that 1 in front. Times the cosine of, now, 360 times 0 is just 0, plus 0 is still 0, divided by 3 is still 0. So that's going to be the cosine of 0 degrees plus I sine of 0 degrees. Now, if I write that in rectangular form, okay, cosine of 0, right? You can do that in your calculator as long as you're in degree mode, but cosine of 0 is 1, and sine of 0 is 0. So that'd be 1 plus 0 I, which is really just equal to 1. Okay, that's one of the cube roots of 1. Makes sense, right? The cube root of 1 is 1. Okay, now let's do another cube root of 1. So that's 1 times the cosine of 0 plus 360 divided by 3. Now 360 divided by 3, I'm typing it in like I don't know it, but I do know that's 120 degrees plus I times the sine of 120 degrees. Now if I change that rectangular, I have to do 1 times the cosine of 120. Okay, so the cosine of 120 degrees, make sure you're in degree mode, is negative 0.5. Okay, the sine of 120 degrees is 0.866, or I'm going to put plus 0.9i. I'm just going to round to the 10th place. So that is another cubed root of 1. Crazy, huh? And then z2 is going to be 1 times, it's going to be the cosine. Now, remember, 2 is my k value. So that's going to be 360 times 2, which is 720 plus 0 divided by 3. So 720 divided by 3 is 240 degrees plus I times the sine of 240 degrees. That's polar form. Now, if I put that in rectangular form, I have to multiply that out. So that's 1 times the cosine of 240. And the cosine of 240 degrees is negative 0.5. And then the sine of 240 degrees is minus 0.9i. Okay? Now, if I graph those, would those be, you weren't asked to graph them, but now I'm very curious. Okay, I want to make sure it's right. So 0 degrees, so that's my 1, 0. It's the first one. Negative 0.5, 0.9i, and that's at 120 degrees. So that's about right here. Okay, and that in rectangular form it's negative 0.5, 0.9. That looks about right to me. Now this was negative 0.5, negative 0.9, which is right here. Did those divide the circle into 3 equal segments? They appear to, so I'm happy with this. Okay, finally, just a little bit interesting stuff. This is the last page of your textbook. And now you probably saw the graph that I had on the opening page. That is one of these things called a Mandelbrot set. This is the opening picture. The one on the far right is the opening picture in the textbook, an old edition of your textbook. If you pulled the textbook up now, it's going to be a different Mandelbrot set. And then over here is also an example of a Mandelbrot set. And I'm just going to read to you what this says because it's interesting. It says the set of all complex numbers for which the sequence, now a sequence is a list of numbers, okay? So the first one is z, just a complex number z, and then notice if you square it and add it to itself. Okay, so you square it and then add itself to it. And then you take that result and you square the one before and add z to it again. And then you take the square the one before it and add z. If you keep doing that, okay, it's called the Mandelbrot set, okay? It says plotting these complex numbers in the complex plane results in a graph that is like bug-like. If you look to the left, that's what they mean. It looks sort of like a bug, okay? Colors can be added to the boundary, which means the edges of the graph. At the boundary, color choices depend on how quickly the numbers in the boundary approach infinity when substituted in the sequence shown above. It says the magnified boundary is shown in the introduction to this section, which is top right over here. All right. It includes the original bug-like structure as well as new and interesting patterns. It says with each level of magnification. So they're saying if you just zoom in to just a little bitty part of this graph and then zoom in more and zoom in more, you're going to see repetitions of this same shape over and over and over. And it's an idea in mathematics called chaos theory, which chaos in math doesn't mean just chaos like we normally think of the term chaos. It's unpredictable repetitions that follow the same pattern. It's a little bit confusing, but very interesting. It says, with each level of magnification, repetition and unpredictable formations interact to create what has been called the most complicated mathematical object ever known. So if you ever just Google Mandelbrot set, you'll see some of the most interesting pictures. I was a big fan of the one that I put at the beginning. It's just something called a Mandelbrot set. So that's a use of these complex numbers, probably not a use that you would think about it comes in handy, but it really makes some cool images. All right, so I hope this goes well. If you have questions about the homework or anything else, please let me know. I'll probably do a few videos on some of the homework problems, and if I haven't and you have questions about a particular one, let me know, and I'll post a video about that particular homework problem. I hope you have a great day.